NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will decode an important rule for inequalities with even roots. The idea appears as a short line in many textbooks, but we will make it visual and intuitive. Step 1. Here is the given condition. For a natural number n, the 2nth root of f of x is less than the 2nth root of g of x. We will keep everything symbolic at first. Step 2. Why does this inequality tell us something simple about f of x and g of x? Because every even root function is defined for non-negative inputs and is strictly increasing there. We will visualize this with the square root curve as a representative even root. Here is the graph of y equals square root of x on x greater than or equal to 0. If it is less than b and both are non-negative, then square root of a is less than square root of b. That is the monotonic behavior that preserves the inequality direction. Step 3. Translate the picture back to our symbols f of x and g of x. Because we used an even root, both inputs must be at least 0. So f of x is greater than or equal to 0. And since the even root is increasing on those inputs, the original inequality is equivalent to f of x less than g of x. That gives the compact two-line answer. Quick check with numbers to cement the idea. Suppose f of x equals 16 and g of x equals 25. Then square root of 16 is 4 and square root of 25 is 5, which indeed keeps the less than sign in the same direction. Summary. For any natural number, if the 2nth root of f of x is less than the 2nth root of g of x, then the required and sufficient conditions are f of x greater than or equal to 0 and f of x less than g of x. In this lesson, we solve a radical inequality step by step using domain checks, safe squaring, and a sign chart to finish. Here is the problem. The square root of the quantity 3 over x plus 1 plus 7 over x plus 2 is less than the square root of 6 over x minus 1. First, both square roots demand non-negative radicands. On the left, we need 3 over x plus 1 plus 7 over x plus 2 greater than or equal to 0. On the right, we need 6 over x minus 1 greater than or equal to 0, which means x is greater than 1. Because x is greater than 1 makes every denominator positive, the left radicand also becomes positive automatically. So our working domain is simply x greater than 1. Because both sides are non-negative on this domain, we can square safely. That turns the inequality into 3 over x plus 1 plus 7 over x plus 2 less than 6 over x minus 1. Move everything to the left. We get a single rational expression, less than 0. Use the common denominator x plus 1 times x plus 2 times x minus 1. Expanding the numerator, 3 times x plus 2 times x minus 1 plus 7 times x plus 1 times x minus 1 minus 6 times x plus 1 times x plus 2. Collecting like terms gives 4x squared minus 15x minus 25. The numerator factors nicely. 4x squared minus 15x minus 25 equals x minus 5 times 4x plus 5. So the critical points are -2, -1, 1, -5/4, and 5. Our domain says x is greater than 1, so only 1 and 5 matter for the sign chart we actually use. Let us build a compact sign chart focused on the domain x greater than 1. We test a point between 1 and 5, say x equals 2. The expression is negative there, so we shade the open interval from 1 to 5. For a test point bigger than 5, say x equals 6, the expression becomes positive, so we do not include that region. Therefore, on the allowed domain, the inequality holds for x between 1 and 5, not including the endpoints. The solution set is the open interval 1, 5. Recap. 1. Check the domain of both radicals. 2. Square safely because both sides are non-negative on the domain. 3. Combine into a single rational inequality and simplify. 4. Factor and use a sign chart, then intersect with the domain. That leads directly to x in the open interval 1 to 5. In this lesson, we will solve a radical inequality step by step and visualize each rule. Let f of x be the square root of 8 minus x squared, and g of x be the square root of x plus 2. We want f of x less than g of x, with both sides defined. Step 1. Domain conditions. Each square root needs a non-negative radicand. From 8 minus x squared greater or equal to 0, we get the absolute value of x less or equal to 2 root 2. From x plus 2 greater or equal to 0, we get x greater or equal to negative 2. Intersecting these gives x in the closed interval from negative 2 to 2 root 2. Step 2. Since both sides are non-negative on the domain, we can square the inequality without changing its sense. That gives 8 minus x squared less than x plus 2. Moving all terms to one side produces minus x squared minus x plus 6 less than 0. Multiply by negative 1 to get x squared plus x minus 6 greater than 0. Step 3. Solve the quadratic inequality. Factor x squared plus x minus 6 as x plus 3 times x minus 2. The critical points are negative 3 and 2. Because the parabola opens upward, the expression is positive outside the roots. So the solution is x in the union of negative infinity to negative 3 and 2 to infinity. Step 4. Intersect the quadratic solution with the domain. The domain is from negative 2 to 2 root 2, closed. Intersecting with the set outside the roots leaves the open interval from 2 to 2 root 2. The right end 2 root 2 is included because the inequality still holds there. Quick endpoint check. At x equals 2, both sides equal 2. So the strict inequality fails and 2 is excluded. At x equals 2 root 2, the left side is 0 and the right side is positive. So the inequality holds and the endpoint is included. Therefore, the final solution set is open at 2 and closed at 2 root 2. Summary. We enforced both domains, squared safely, solved a quadratic inequality, and intersected with the domain. The solution is the interval from 2 to 2 root 2, open at 2, and including 2 root 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.